Have you ever wondered why two galaxies can spend billions of years spiraling together, only to seem to freeze once they get far enough apart? It sounds impossible at first. If gravity is an all-the-way-in kind of force, why would attraction ever turn into hesitation? And here's the twist that makes this problem so captivating to astronomers right now. Our usual intuition about galaxy mergers breaks at large scales, where something like a dark energy horizon starts to matter. Imagine reaching a point beyond which the universe itself refuses to let more progress happen. Not because galaxies lose mass, not because gravity suddenly stops, but because the space between them begins expanding in a way that can outrun their ability to bind. Today, we're going to follow that open loop all the way to its consequence. Mergers that stall at huge distances, as if the cosmos has a boundary condition written into it. To understand the before state, picture how we normally think about large-scale structure. Galaxies form within a cosmic web of dark matter. Dark matter halos pull gas and stars into galaxies, and those halos can merge. If two halos come close enough, their mutual gravity overcomes expansion, and then dynamical friction and tidal interactions drain orbital energy until the galaxies coalesce. For decades, cosmologists modeled this with gravity plus a smooth background expansion driven by dark energy. In the simplest view, dark energy doesn't clump on galaxy scales, so it mainly acts like a uniform pressure that accelerates the expansion of the universe. If it's uniform, it shouldn't pick sides between nearby objects. Yet observations show something puzzling. Some pairs and groups of galaxies appear to remain separated longer than gravity-only calculations predict, especially at larger separations and in low-density environments where acceleration is strongest. Here's the core mechanism. Take two galaxies sitting in the expanding universe. Close together, gravity wins quickly. The galaxy's mutual pull becomes the dominant clock, and they can decelerate the local expansion, turning it into a collapsing dance. But there's a race. On one side is the inward pull of gravity, which scales roughly like GM squared, getting weaker with distance. On the other side is the expansion of space, characterized by the Hubble flow, which increases with distance farther objects recede faster. If you move the galaxies farther apart, the outward recession rate grows until it becomes comparable to the time it would take gravity to pull them together. At that tipping point, the system crosses from a bound regime into an unbound one. The transition isn't a hard wall you can point to with a ruler, it's a boundary in phase space, a horizon, meaning that causal contact and affected binding change character. Now add the role of dark energy. In a universe with a cosmological constant, the expansion accelerates. That acceleration makes the Hubble flow stronger at late times, so the distance where gravity can still win shifts. The critical separation, often called a turnaround radius in related contexts, acts like an effective dark energy horizon. Beyond it, even if two galaxies were once approaching, the accelerating expansion can prevent them from ever completing the bound orbit that would lead to a merger. The galaxies might drift, form a loose pair for a while, and then slide into the expanding background. Their relative motion becomes dominated by cosmic expansion rather than mutual attraction, so orbital energy isn't drained into a coalescence. Instead, the separation grows. Think of it like two people trying to converge while standing on a treadmill. Nearby, you can walk toward each other, but as the conveyor speeds up with distance, there comes a point where your inward effort can't keep up with the outward motion. Gravity is walking. Dark energy is the speeding treadmill. Discovery-wise, this idea crystallized as surveys improved and cosmological models became precise. Simulations that included dark energy showed that mergers are not guaranteed outcomes of initial proximity. Infall into halos happens, but the probability of eventual merger depends on whether the pair ever becomes gravitationally bound against the expanding background. Observationally, astronomers use redshifts to infer distances and velocities, then compare pair counts and clustering patterns to what models predict. The signatures of stalled merging show up statistically. Certain configurations are more common than gravity-only merger rates would allow, especially when the environment is underdense and the cosmic expansion dominates. Over cosmic time, the universe's acceleration shifts the balance, making the last chance to merge happen earlier. That's why the phrase beyond light speed matters as more than a speed limit. Even if the galaxies themselves never cross any local speed limit, the region that can influence them through causal processes and maintain binding effectively shrinks, because the accelerating expansion stretches space in a way that changes which signals can keep the system coordinated. So what's the broader implication? First, mergers are engines of galaxy evolution. They trigger starbursts, redistribute angular momentum, grow bulges, and help build the massive ellipticals we see today. If mergers stall at large separations, then dark energy doesn't just change the fate of the universe, it changes the timeline and frequency of how structures assemble. Second, this provides a consistency test for the nature of dark energy. If the horizon effect predicted by a cosmological constant describes what we observe, then the simplest explanation survives another round. If not, it would hint that dark energy behaves differently, perhaps clustering, evolving with time, or coupling to matter in subtle ways. Third, there is a conceptual payoff. It forces us to separate light speed from causal contact. Causality in an expanding universe isn't only about the speed of objects, but about the geometry that determines which events can influence each other over time. A galaxy can remain locally slow and still be swept beyond the effective gravitational reach of another, because the background expansion modifies the rules of long-range organization. Finally, bring it home. We started with an open question. Why do galaxy mergers seem to stall? The answer isn't that gravity fails. It's that gravity competes with a cosmic opponent whose strength increases with distance as the universe accelerates. Close pairs bind and merge, far pairs drift, because dark energy makes the expanding space between grow faster than their mutual attraction can overcome. That creates an effective dark energy horizon, a boundary in which the universe's expansion changes the outcome before the merger ever has a chance to complete. The deepest part is that this horizon isn't a physical barrier. It's an emergent consequence of geometry and timing, and it suggests a humbling thought. Some futures don't happen not because events are forbidden locally, but because the universe organizes itself so that the necessary connections never stay connected. If you want more of these, The Cosmos Rewrote the Rules explanations. Subscribe for the next one.